All right, and we are live. Let's see. Today we have an exciting session. The first one by Sebastian from Asymmetric Research, and the second one by Evgeny from the foundation. So Sebastian is gonna, let's bring him on. There we go. All right, and this one a bit bigger. There we go. All right, so people should see now the main Sebastian's presentation. So, like I said, the first one is around security best practices, and this is all in the context of Sigma, the Sigma Sprint event, the builder competition, which actually kicks off on Monday next week. So these are kind of pre-builder, pre-hackathon sessions that folks can follow along to dive into some of these topics, kind of get in the mood, get warmed up, to see what, to maybe also get some inspiration what to build. And in your case, Sebastian, to upgrade their security best practices, I would assume, right? So the word is yours. Kick it off. Go ahead and have some fun.
Thank you very much, Urban. It's a pleasure to be here. Thanks for having me. I'll start off with a very brief introduction about asymmetric research for those of you who don't know the company. Um, the mission is to enable secure innovation, and this is done with a very long-term partnership. And if you have these long-term partnership, you align incentives and you can do things that you cannot do with a typical Web3 security company that maybe only does upgrades or one particular service. So what we do in more detail is that we do deep security research. So our researchers up to date have contributed to responsible disclosures of over $1 billion of loss avoidances. We also do security engineering, which means that we don't just find bugs, we also help you fix them, and we build stuff securely. We do incident response in case something happens, and you know some hack happens. We're the first ones to help in those kind of situations. And last but not least, we run infrastructure. We run blockchain infrastructure, so validators on many different blockchains, some of which are mentioned here, Solana, Aptos, and Sui, and we do that, of course, in a very secure and performant way. But enough about asymmetric research. I'll dive into the meat of this presentation, which has to do with common security vulnerabilities, right, in blockchain applications and how to prevent them. So you might be familiar with blockchains. One of the most popular one is, of course, Ethereum. And I've just, looked online regarding what are the most well-known and most dangerous types of vulnerabilities on Ethereum, right? And I have here like a top 7 list. Of course, the list is very long. It didn't fit on one slide, but here's like sort of the most frequent ones that I encountered for Ethereum. Probably many of you have heard about reentrancy or oracle manipulation in combination with flash loan attacks, unchecked return values, insufficient input validation, front running, and so on. Now on Solana, I did the same thing and I came up with a different set. Like of course there are similar issues or vulnerabilities on both blockchains, but it was interesting to see that the top 7, looks a bit different. Even though there's some overlap when it comes to input validation, because like missing, like signer check or missing account writable check and so on are also a form of input validation, but you also have different ones, more unique ones that are specific to Solana. So, I couldn't decide which ones should I be talking about in this presentation. And then, one thing that I thought about, what's the common, thing that everyone in this program will want to learn about, right? And then I realized, okay, it's simple. It's just building using Wormhole on top of Wormhole, right? So then it's easy. I'll just focus on the common developer mistakes, which happen when you're using a framework and a cross-chain messaging system such as Wormhole. And those are, I'm just focusing on these top five ones: message spoofing attacks, replay attacks, type confusion, code injection, and chain reorg. These are very common attacks that happen if you're using Wormhole for the first time. So in the remaining of this presentation, we're going to go into detail for each of these five different attacks. And please feel free to write any questions in the chat. I have the chat open here next to me whenever you have something. So let's start with like a brief overview of the architecture. I'm pretty sure you might have seen this before. The main takeaway here, if you look at the Wormhole architecture, is that you should keep in mind that it only, between quotes, because it's not an easy thing, it only passes messages between chains, between a source chain, which is indicated here on the left, and a target chain, which is indicated on the right, using a trusted network of guardians operating under proof of authority consensus. It does not do any specific security checks for your application. So that is your responsibility as a developer. And this is very important to keep in mind. You cannot assume many things, right? There's a lot of implicit assumptions here when you're building on top of Wormhole, and we're going to go through them and debunk them in the next slides. So let's start with the first attack, which was on the top 5 list a couple of slides earlier: message spoofing attacks. This is a very high-level depiction. You basically have a malicious relayer here on the left. And what a malicious relayer can do is that, it could create a fake VAA, which is basically a message, a verifiable, message on a different chain. And it could fake it and relay it to a target chain. And if the contract that is picking this VAA up on the target chain does not do verification, it can get into serious trouble and lose funds. So how does this look in code? In the code, how you do this verification is using this method called parse and verify VAA, or parse and verify VM. VAAs were called VMs, verified messages, before, but VM had a lot of I guess like clashes with virtual machine, so it was changed to VAA. But that message remains because they didn't want to break any legacy code by changing the interface. So you basically receive a message on the target chain as an encoded message, and what you should do is call this parse and verify VM on the message. It returns the wormhole VM structure. It returns a Boolean indicating whether this is a valid VAA. And if it's not a valid EAA, it gives you a reason why it's not. So, of course, the first check you should do there is to check if it's valid. And if not, you should revert and provide the reason. So, this is definitely a must-do when you're receiving a message on a target chain on your wormhole application. So question, and I really want to keep this a bit interactive so that people don't fall asleep. I'll wait until anyone, writes an answer to this question in the chat, but are message spoofing attacks still possible after we're checking whether the VAA is valid using this parse and verify function? What do you think? Let's see, is anyone there? What's the meaning of VAA? I think VAA stands for verifiable Uh,
Verified action approval, if I'm not mistaken.
action approval, exactly. I was like, yeah, verified action approval. It's basically a verified message. I think, the original name was a good name. Unfortunately, it had a lot of clashes, but it basically is a message that has gone through the the Guardian network. So it was approved by the Guardian network. So regarding this question on this slide, anyone have an opinion? Very silent. It's very silent. No one? Is there anyone there? I saw some messages before we started the presentation in the chat. So someone must be there. So what do you guys think? A yes or a no for this one? Is there anyone in the chat, Urban? I'm not sure. Yes. Okay, it's still possible. Indeed, it is still possible. And the reason why it's possible is that you also need to check where the message is coming from. Is it coming from a trusted source? In Wormhole lingo, a trusted source is called a peer. And just to illustrate it, you have this contract on a target chain, and this contract might be receiving a VAA from chain one, with like a certain um, address, which is a good one. It's a good VAA. This is a trusted peer, and it might be receiving a VAA from the same chain, but from an address which it doesn't trust. The way in which you check this in the receive message function, after you've checked the validity, is that you look up inside of your peer's mapping, you check if the peer at index corresponding to the chain ID of the emitter of the message you received or you decoded before is equal to the emitter address of that same structure. And if they're not, then it's an untrusted peer. So this is a very excuse me, a very simple check. Um, but it's a must-have because otherwise you're basically accepting messages from untrusted sources, and that could lead to a lot of damage if untrusted sources can send you um, like random messages or like messages that you're processing in your application, and you might be giving out funds or transferring funds based on those messages. So definitely check the source. And now, add on to that question before. So if we're checking the validity of the message and we're checking the source, are these message spoofing still possible? What do you guys think? Again, I'll wait for someone to write something in the chat. Are they still possible or not? Just a yes or a no is fine. I see. Oh yeah, I think like there are two yeses. No, okay. Someone wrote no. The answer is still yes. So One other thing you should check before you start processing the message is whether the message is intended for your application. And the way you do that is you might look at the payload of the message. Here's that VAA structure, also known as VM. It has different, fields, some of which we already were using in the previous slides, like the emitter chain ID and the emitter address. But it also has the payload, right? And in the payload, you can look a bit deeper whether the destination is your contract or not. So a VAA might be coming from a trusted source, it might be valid, and it might be intended for your contract, which let's say is AAA, but it might also, be coming from a trusted destination. It might be valid, but it would be intended for a different application. So in the code, you would basically decode the payload, and from that, using that function, you get the destination address and the destination chain, and you make sure that the destination address matches your contract, the contract that you're currently executing, and it also matches the chain ID. This is, of course, for especially for like many EVM chains where this contract might have the same address. All right, now again to our question. Are message spoofing attacks still possible if we're checking, the validity, the source, and the destination? What do you guys think? Again, just a simple yes or no in the chat. Any opinions? No. Okay, that's right. So we're gonna stop with like the message spoofing attacks for now. Indeed, those are three things that you should definitely check. Let's move on to other types of attacks in our top five. The second was replay attacks. Now, in the case of replay attacks, it's very interesting. You might be checking all of the things that we discussed about before. You're checking if the VAA is valid. You're checking the source and the destination. But even in that case, a malicious relayer, could see when you're receiving a VAA and then send it again later, the same VAA, because maybe you did something like transferring funds to a particular address when you saw that VAA, and they want you to do it again, even though there was nothing happening on the source chain. They would just take the VAA and relay it again, and maybe you do the same thing again, right? So in order to prevent replay attacks in the code, what you should do is you have this replay check mapping, which is basically just a mapping from a hash of the message to a Boolean. And it's basically just flags, right? And whenever you see a VAA, you check whether you've seen it before by looking up, using that hash of the in this mapping called replay check. And it should be false, right? If it's not false, then you've already seen it, and you should just ignore it. You should stop executing because you've already seen it. And if you haven't seen it before, make sure to set it to true because now you've seen it. So if it comes again, you should ignore it. It's as easy as that. Now, we can put both the countermeasures that we use for anti-message spoofing and anti-replay into one big function, called, the function is where you receive the message. And let's just go over the steps again. You parse and verify the VAA, then you check its validity. You can do that in whatever order you want. You check if you've seen it before, This is the replay protection. You check whether it's coming from a trusted source, so a trusted peer. You decode the payload, and then you check if it's intended for your application on this chain where you're currently on. And then you can start doing, like the application specific processing, right? If you remember the takeaway that I had when I showed the wormhole architecture, I was saying, be careful because wormhole only sends the message. It doesn't do any application specific, you know, security checks. And these are, like not necessarily application specific. They're pretty generic for many applications. These things that we've looked at up to now. But the question is, are we safe at this point, or do we need to do more? What do you guys think? Safe or not safe? I'll wait for an answer in the comments again, in the chat. Anyone? What do you guys think? People still with me? Safe or not safe? Not safe, indeed. So, it definitely depends on what exactly your application is doing, but a valid VAA does not mean that it's safe for your app. So, the generic message passing bridge does make a few assumptions about, what developers are doing, but you still need to validate the payload for your app. So you need to look at it in more detail. And what could happen there are type confusion attacks. This could be very bad for your app. And this is an illustration of how those type confusion attacks look like. So let's assume that your smart contract, your application, has two endpoints that you've defined. One endpoint is basically giving you the updated price from an oracle, and the second endpoint is giving you the voting weight for something, right? And you've clearly defined these two endpoints, but then what happens if a VAA is coming, a VAA which was meant, this one is good, but this one at the bottom here, this one was meant to come through endpoint 2, but for some reason, it's coming through endpoint 1, and you're interpreting this 10 as the new price. This could be very, very problematic. Therefore, you need to check, the type of the payload, right? And here's a very good example from the Wormhole bridge, where the payload has different types, and on the left-hand side we just have a simple transfer, and the payload ID in that case is equal to 1. And on the right-hand side we have a transfer with an additional payload at the bottom here, which is an arbitrary payload. And in this case, the payload ID is equal to 3. So this way your application knows, okay, am I expecting to have this additional payload of arbitrary length at the end or not? And even the structures are slightly different here. Here you have a fee, and in this case you don't have a fee. You have a from address and a payload. So this is just an illustration of how it looks like in code, and just like a drawing. But the main takeaway from what we've seen up to now is that you need to do a lot of input validation when you're using Wormhole. Some of the worst things can happen, if you're not doing proper input validation. So don't leave any assumptions unchecked. You want to check, that the message is only delivered once, so you don't suffer replay attacks. You want to check the source is trusted. You want to check, if you're the intended sender. Sorry, even the destination, right? You also want to check if you're the intended destination, and so on. You can also do length checks if you're expecting a specific. Don't make an assumption that it's going to be of that length. Do the explicit check, and also check for same values in the payload. So something that you're expecting. Don't assume that the end users will always send a value between 1 and 5 if it's of type uint 8, right? They can send a much larger value. So definitely check for those kind of sane or expected values. And overall, you should just trust nothing and verify everything in your code. All right, so we focused a lot on receiving messages on a target chain because that a lot of things can go wrong there. But do you think anything can go wrong when sending messages? Like, do you think like you program the app which is sending messages, and like Wormhole takes care of sending them? Can anything go wrong? Like, what do you think? Yes or no? I'll wait for an answer in the chat. Can anything go wrong when sending messages? Yes, thank you. So one thing that can go wrong, and it was number 4 on the list, is called the code injection attack. So here's a piece of vulnerable code when sending messages. Can anyone, spot what is risky if we use this code snippet? Anyone in the chat willing to give it a shot? I'll wait for a few seconds. I guess not. So what happens here is that you're allowing the end user to provide too many inputs. And this end user might be malicious. So allowing the end user to specify the wormhole address, for the wormhole core contract, and allowing the user to specify the consistency level could lead to problems. Let's just start with the first one. So if a malicious address is passed instead of the correct wormhole address, what could happen is that it could, of course, be an attack contract. And of course, it's used to, for instance, verify message signatures, as we saw before. And the signature could be on a large transaction, a large transfer of funds from one account to another. So what this malicious contract that is passed in could do is would just skip signature verification. It would just say it's valid, no problem. Just process it, no worries. And of course, this could lead to a major loss of funds. I'm not sure if any of you have recognized that this is exactly one of the like vulnerabilities which led to a over $200 million loss back in 2021 in the ecosystem. Just allowing someone to specify the address of a contract where they should not have been able to specify it. So this particular problem has led to huge losses in the past. This is what you should do. You should only let the user send the message and you use your trusted wormhole address instead. You only, the only thing you trust the user to specify is just the message you want to send in the VAA and nothing else. But we had another parameter in the code before And that could lead to chain reorg attacks, which is, the last one. So in order to understand chain reorg attacks, let's just quickly look at consistency levels. Some of you might already be familiar with them, but these are the three consistency levels which are, used when you're building on top of Wormhole. And of course, they might be all good for different purposes. So not for all purposes. So let's assume, like we have an application where latest could be the one that you want to use, right? And the issue with latest, this consistency level, is that if you're using a block with this consistency level, the chain might reorganize itself, and the block itself might not be valid anymore. So if you're using latest in your application on the target chain, make sure you understand that whatever is in that block might disappear. You might want to use it for some particular reason. If it's not a big, deal, you're not making any huge transfers based on it. Maybe you're just generating a number for something, right? And then you can use latest, or you want to do something, with data as soon as possible, and that's when you use latest. But you don't want to, like make large transfers when you're using latest. At least it's very risky from my perspective. The second consistency level is called safe. And in this case, you already have received attestations from 2/3 of the Ethereum validator set. So it's very unlikely that the chain will be reorganized. And you can feel a bit more comfortable. There's still a small chance, but you might be willing to take that risk in your particular application for a higher fee, right? Because you can act faster than if you use the strongest consistency level, which is finalized. And in this case, it's extremely unlikely that the chain will be reorganized. So in this case, you can confidently transfer funds if you're receiving data from a finalized block. You can be pretty sure it's fine, right? So back to our unsecure code snippet. If the end user is allowed to pass in the consistency level, and the user passes it incorrectly, they might pass in finalized when using a block which is actually at the consistency level latest in reality, but they're claiming it's finalized. So if an attacker withdraws funds on the destination chain based on the fact that this message was considered to be finalized, and after a few minutes the transaction on the source chain is rolled back because the chain is reorganized, then the attacker can also withdraw funds on the source chain, and now the attacker has withdrawn the same amount, maybe a large amount, on both source chain, destination chain. They exit using some centralized exchange, and now they've doubled their money, right? So this, and they've basically depleted maybe a lot of your funds from your application, from your cross-chain application. Might be a DEX, might be a lending platform, who knows? So this is very important. It's a small thing, many people consider, oh, it's consistency level, it makes sense, whatever, but it could have dire consequences. So again, instead of allowing the user to pass in the consistency level, just allow them to pass the message, because that's the only thing you can trust. You're going to be validating the heck out of this message on the target chain, as we've seen at the beginning of this presentation when we went over the first three types of attacks. So that's why they should be able to send the message. Otherwise, the application doesn't even make any sense if you're not able to send at least something. All right, so that pretty much concludes what I wanted to convey in this presentation. As a summary, the best practices when you want to code something securely using Wormhole is that you don't trust any user inputs. You validate, the validity, you validate whether you've seen the message, the source, destination, everything. And also application specific stuff, right? You verify and you check the assumptions that you've made when you built the application. Is the payload ID correct? Is this the type of message that I'm expecting to contain the oracle price, or is it a type of message where I'm expecting the vote weight? The third one is, of course, don't let users provide inputs that they shouldn't be able to provide, like the wormhole address or the consistency level in some cases, right? Because it could lead to massive hacks. And last but not least, just to double check everything and make sure that, you haven't forgotten any of the checks, you can write a proper test suite where, you don't only check the positive cases, you also check edge cases where you're sending malicious input. So when you write tests, it's super important that you're not writing the happy path tests, because those will probably pass. Always think like an attacker and try like crazy inputs um, to the tests, such that the application should maybe catch them and fail and write some error message. Those are really quality tests. That's it. Thanks a lot for your attention. I guess like this was a bit faster, but I definitely would like to leave some room for questions.
Yes, thank you very much, Sebastian. This was very, very informative. I think generally security-related sessions are really well received. So thank you very much for running us through. Let's see. We do have a question box if people have questions.
Yes, I see.
Ooh, Aman, this might be very specific. I might have missed this one. Can we also transfer NFTs and their ownership to other chains using this? I don't know what this refers to, though. We might have missed this one.
Yeah, it wasn't part of the presentation, but as a general question to, an application that uses Wormhole, there is an NFT bridge, so you can transfer NFTs using Wormhole. If that answers the question, I'm not sure.
I don't know. Maybe Aman, if you wanna like double click on that, feel free to put it in the chat box. Otherwise, reach out to us. We're around. Yeah, I think let's wrap it up. Sebastian, this was fantastic. Thank you very much. Really, really good content. Everything that you've just heard and seen is going to be available on YouTube. I think we actually, as a matter of fact, we live stream this to YouTube as well. So thank you very much, Sebastian. This was a great session. Thank you very much, everybody, for listening. We're going to have about a 20-minute break, and then we're going to welcome Evgeny for a deep dive into the Wormhole tech stack. So I'll see you all in about 20 minutes. Thank you. Bye.
Thank you very much. Bye.